Imagine an artificial intelligence agent writing its own code, provisioning its own hidden infrastructure, and executing tasks across multiple of your AWS accounts while you sleep.
Yeah, I mean, if you are a security engineer listening to this, your alarm bells are probably ringing right now.
Oh, absolutely. It sounds like a complete compliance nightmare.
Hmm.
Welcome to the deep dive. Today, we are sorting through a massive stack of 41 distinct AWS updates that were pushed out between June 22nd and June 26, 2026.
And, if you review this week's architecture changes, these updates are not just routine maintenance.
Right.
They signal three specific structural shifts across the platform. We're seeing the introduction of a completely new primitive for compute isolation, the direct embedding of agentic AI right into the AWS control plane, and, well, a series of very strict networking and observability changes meant to govern all of this.
Exactly. Our mission is to extract the actual architectural signals from the noise of the standard release documentation. Okay, let's unpack this, starting exactly where every major shift begins, which is the compute layer.
Right, so the compute layer is seeing a massive physical expansion this week. But it's not just about raw geographic footprint. AWS is deploying entirely new processor architectures that fundamentally change the limits of memory-intensive workloads.
Yeah, like the silicon expansion.
Exactly. If we look at the new RAG instances, which are powered by the AWS Graviton4 processor, they are now available across Thailand, New Zealand, Cape Town, Milan, and Calgary.
Wow, that's a huge rollout.
Yeah, and these instances provide up to 3 times more virtual CPUs, scaling all the way up to 48x large, and they offer up to 1.5 terabytes of memory compared to the previous Graviton 3 generation.
Right, and we see a very similar pattern with the x86 architectures, too. I mean, it's a push for absolute peak memory and specialized processing. Like, the C7a instances, which utilize the 4th generation AMD EPYC processors, are now online in the Singapore region. They bring AVX 512 and bflt 16 support, which is critical for machine learning inference, along with DDR5 memory.
And then you have the M8a instances in Mumbai, running the 5th gen AMD EPYC Turin processors at a massive 4.5 gigahertz maximum frequency.
Yeah, and for network-heavy requirements, the CA instances are expanding to Ohio and Ireland, delivering, 600 gigabits per second of network bandwidth?
Exactly.
But instead of just memorizing instance names, notice the overarching pattern here. AWS is pushing capacity to the absolute extreme.
Oh, sure. Take the new U7in-24TB instances that just went active in Seoul.
Right.
These provide 24 TB of DDR5 memory and 896 virtual CPUs, specifically because workloads like SAP HA require entire massive databases to be loaded directly into RAM just to function efficiently.
Yeah, so those hardware updates provide the necessary scaling options for monolithic applications, but the fundamental architectural shift in compute this week is not about size.
No, it's about isolation.
Right.
This week marks the general availability of AWS Lambda MicroVMs. This is a completely new serverless compute primitive.
Yeah, I saw that.
It provides full virtual machine-level isolation built directly on the open-source Firecracker hypervisor while maintaining near-instant launch times and preserving execution state for up to 8 hours.
Wait, let me stop you right there. I need to question the mechanics of this because it sounds like it defies the standard CIP theorem of compute.
How so?
Well, historically, in distributed systems, there was always a strict trade-off. If your workload required strong isolation, you incurred incredibly slow cold starts because you had to boot a full virtual machine kernel from scratch.
Right.
But if you wanted fast execution and fast cold starts, you used containers or standard Lambda functions, which share the underlying kernel state and hardware. So how is this microVM primitive fundamentally different from a standard Lambda function or an AWS Fargate container, particularly when it comes to network routing?
Well, it is different because of how it exposes the underlying virtualization. Standard Lambda abstracts the execution environment.
Okay.
If you run a standard container on Fargate, a severe kernel exploit could theoretically compromise the shared underlying node. But Firecracker, which powers these new micro-VMs, strips out all the legacy device drivers and bloated hardware abstractions found in traditional hypervisors like QEMU.
Oh, I see.
This allows it to boot a secure hardware virtualized boundary in a fraction of a second. But why this matters right now is because developers are building complex, multi-tenant applications, things like automated vulnerability scanners or AI coding assistants that are forced to execute untrusted, user-provided, or AI-generated code.
Ah, so you need a sandbox that boots instantly but strictly cannot be escaped.
Precisely. With Lambda MicroVMs, you create an image from a standard Docker file, and AWS provisions a dedicated hardware-backed Firecracker microVM for that specific execution job.
Wow.
Furthermore, each microVM is assigned a dedicated HTTPS URL supporting HTTP2, gRPC, and WebSockets.
Wait, native ingress?
Yes. This natively solves the untrusted code execution requirement. You're getting a hardware virtualized boundary with direct isolated network ingress per session, eliminating the need to maintain your own complex fleet of isolated EC2 instances just to run untrusted code safely.
Okay, so if we're trusting AI to execute raw code in these highly isolated micro-VMs, I mean, the immediate next question is, what happens when that AI needs to pull data from or write data to a completely different AWS account?
Yeah, exactly.
That brings us right to our second architectural theme. We are seeing AWS actively transition artificial intelligence from a passive interface where you ask a question and get a text response to an active cross-account infrastructure operator.
We are definitely seeing the compliance barriers being removed to allow for this.
Yeah.
OpenAI GPT, OpenAI GPT OSS, and NVIDIA Nemotron models running on Amazon Bedrock have now achieved FedRAMP High and Department of Defense Impact Level 4 and 5 approval in the AWS GovCloud US regions.
That's massive for public sector workloads.
It really is. It authorizes these specific models to process highly sensitive classified government workloads.
Yeah.
But the real structural change you mentioned is with Amazon Bedrock Agent Core Memory. It now supports native cross-account access via resource-based policies.
Right. This means the memory data plane APIs for the AI agent can now write directly to Amazon S3 buckets, Amazon SNS topics, or Amazon Kinesis data streams that are located in entirely separate AWS accounts.
Yeah, it's a huge shift in autonomy.
And we also see this autonomy showing up in infrastructure management tools. Like Amazon MSK has introduced AI agent skills, allowing tools like Hero and Claude Code to autonomously analyze, size, and migrate your Apache Kafka clusters.
Right.
The migration assistant for Amazon OpenSearch now uses AI to execute complex live data migrations from Seoul and Elasticsearch environments. And Anthropic's Claude Tag is now available in the AWS Marketplace, allowing multiplayer Slack integrations where Claude operates under its own channel-scoped identity.
Yep.
But going back to Bedrock Agent Core Memory, if you are a security engineer listening to this is where the panic sets in.
Oh, absolutely.
Allowing an AI agent to read and write memory across AWS account boundaries introduces a massive surface area for data exfiltration. I mean, if a user injects a malicious prompt or the underlying large language model hallucinates and generates an unexpected sequence, and that agent has cross-account write permissions to an S3 bucket, how is this risk managed at the architectural level?
What's fascinating here is how AWS is deploying mathematical verification to mitigate that exact non-deterministic behavior.
Okay, mathematical verification.
Right, because you cannot secure a generative AI model using traditional static rules because the output is constantly changing. So this week, AWS updated the automated reasoning checks in Amazon Bedrock guardrails.
Oh, I see.
Automated reasoning does not rely on guessing what the AI might say. It uses formal logic and automated theorem, proving to mathematically validate the generative responses against strict, predefined security policies.
Wait, I want to make sure I fully grasp this. The update introduces two new workflows for this mathematical validation.
Yes.
First is iterative policy improvement, where the system deduces the necessary policy changes needed to pass natural language tests. And the second is ambiguity reduction, which automatically refines variable descriptions and type definitions to prevent the LLM from making ambiguous logical translations.
Correct. Let's look at the mechanics of ambiguity reduction. When you write a natural language policy restricting an AI agent, human language is inherently flawed and ambiguous.
Sure.
An LLM might misinterpret what restricted data actually means. So the formal logic solver maps out all possible mathematical states of that policy. If it finds a logical gap where the agent could theoretically bypass the rule, it forces the refinement of those variables.
Oh, wow.
Yeah, by utilizing formal logic to validate the outputs and automated the refinement of those policies to eliminate any logical ambiguity, security engineers can establish a deterministic, mathematically verifiable boundary around the AI agent.
That's wild.
The architecture dictates that the non-deterministic output must pass the strict mathematical proof of the guardrail before the cross-account API call to the S3 bucket is ever authorized.
That is incredible. It enforces strict mathematically proven execution parameters before the cross-account boundary is ever breached.
Exactly.
But, as these AI agents start operating across multiple accounts and these highly isolated micro VMs start spinning up by the thousands, controlling the network perimeter itself becomes absolutely vital, which leads to a massive quality of life update regarding network routing and governance.
Yeah, the most critical update in the networking space this week is a direct modification to the default behavior of the AWS network firewall.
Right.
The default stateful action for new firewall policies has been changed from application drop established bidirectional to application drop established server-directed only.
Okay, wait, I am confused by this. On the surface, bidirectional sounds infinitely safer than server-directed only.
I know it does.
If you were dropping malicious traffic, wouldn't you want to drop it in both directions? What was actually breaking under the hood in the TCP state machine that forced AWS to change this default behavior?
Well, it comes down to how strict intrusion prevention systems handle network latency. Under the previous bidirectional default, the Suricata-based engine running inside the network firewall maintained a very strict state table of every connection.
Right, it tracks the handshake.
Exactly. But because of asymmetric routing or minor network latency, TCP packets sometimes arrive out of strict sequence. If the firewall's state table determined a connection was closed, or if a packet arrived slightly late, it would aggressively drop legitimate server-to-client flow control packets.
Oh, no.
Specifically, it was dropping TCP window updates, keep alive packets, and TCP reset packets sent from the server back to the client.
And because it was silently dropping the server's keep alive attempts, the client application thinks the connection is still open,
Right?
creating a zombie connection that eventually just times out.
Exactly. It resulted in intermittent, highly disruptive connection failures that did not generate standard block traffic logs because they were classified as flow control anomalies.
That sounds like an absolute nightmare to debug.
It made the root cause a nightmare for network engineers to diagnose. So changing the default to server-directed only ensures these specific, legitimate flow control packets are not blocked by default, significantly improving overall network reliability for long-lived TCP connections without requiring manual rule adjustments.
That is a massive relief for anyone managing persistent database connections or WebSocket streams through an AWS firewall.
Absolutely.
We are also seeing important scale updates to identity and routing. AWS IAM Identity Center now supports separate, independent quotas, allowing organizations to manage up to 7,000 AWS accounts and 7,000 applications.
Yeah, that's a big scale up.
And Amazon Route 53 Global Resolver now permits the sharing of DNS views between different AWS accounts using AWS Resource Access Manager, or RAM. This is huge because it allows consumer accounts to associate their own private hosted zones with a shared centralized DNS view without having to transfer zone ownership. It eliminates a ton of administrative overhead and zone duplication.
It really does. And on the strict governance side, Amazon EC2 introduced AMI watermarks.
Oh yeah, the watermarks.
This is a critical feature for compliance. It allows you to embed immutable metadata into your private Amazon machine images.
Okay.
This metadata persists through copying operations and cross-region transfers. So security teams can now enforce allowed AMIs policies based on these watermarks, cryptographically proving the provenance of an image no matter where it is deployed globally.
That's a great zero-trust primitive.
Yeah. Additionally, Amazon Cognito now supports customer-managed KMS keys for data encryption at rest in the Essentials and Plus tiers, giving you full cryptographic control over user identity data.
So we have the compute isolation established with micro-VMs, we have the AI boundaries mathematically secured, we have the network routing fixed and governed. The final piece of the architectural puzzle is observing and managing the data flowing through this entire system without bringing the application down.
This is where we see a systematic removal of operational friction. For example, Amazon EMR Serverless now supports live configuration updates.
Wait, live updates?
Yeah. Previously, if you needed to adjust resources, you had to restart the cluster. Now, you can modify maximum capacity settings or custom image configurations without stopping the running application.
Oh, that's incredibly useful.
New data workloads automatically utilize the updated settings, while your existing workloads continue processing on the original configuration seamlessly until they finish.
In terms of observability, Amazon CloudWatch now supports the assignment of key value tags directly to dashboards, allowing for attribute-based access control and easier filtering across large organizations.
Right.
But the most significant observability update is that CloudWatch Logs now supports managed syslog ingestion. You can route syslog messages over TCP, TCP with TLS, or UDP directly to a VPC endpoint. It automatically parses RFC 5424 and RFC 3164 log formats, extracting structured fields like facility, severity, and hostname, and it does this entirely agentless.
Alongside that, CloudWatch also launched OpenTelemetry Container Insights for Amazon EKS. This provides infrastructure metric extraction at 30-second granularity using standard open-source receivers like CADvisor and KubeState metrics, coming with pre-built PromQL dashboards out of the box.
We also have crucial updates to data movement and specialized workloads, like AWS Backup now executes Amazon S3 cross-account and cross-region copies up to 8 times faster.
Yeah, the way they achieve this is brilliant.
Right. Instead of performing traditional list objects scans on the destination buckets, which, can take hours if you have billions of objects just to figure out what changed, AWS Backup now tracks object events directly to trigger the replication.
Exactly. It's event-driven now.
And Amazon MSK Replicator now supports mutual TLS authentication, allowing secure data replication from external Apache Kafka clusters directly into MSK Express brokers.
Right.
And for highly specialized workloads, AWS Health Onyx added ephemeral storage, providing up to 3,072 GB mounted at the team-up directory, along with support for Nextflow profiles.
Yep.
Finally, AWS Batch added 2 new instance allocation strategies: Best Fit Progressive Ordered and Spot Capacity Optimized Prioritized, which allow you to manually define the exact ordering of your instance types to maximize spot instance savings.
If we connect all of these observability and data movement updates to the bigger picture, they represent a deliberate removal of intermediary fragile infrastructure.
So what does this all mean in practice? Let us look closely at the CloudWatch Managed Syslog update. If this process is entirely agentless and your network devices are routing log traffic directly to a VPC endpoint, how does an engineering team manage high-throughput bursts?
That's the million-dollar question.
Right. If you have a massive farm of network firewalls sending millions of logs via UDP, which is a connectionless protocol that doesn't verify packet delivery, how do you prevent massive packet loss without maintaining local buffers like Fluent or Logstash on intermediate EC2 instances?
Well, by removing the local agent, you actually eliminate the disk I/O and CPU constraints of those intermediate instances entirely.
Oh, interesting.
Yeah, this new CloudWatch update completely removes the need for local buffering on EC2. Instead, the AWS network backbone absorbs the raw UDP logs straight into the central CloudWatch logs control plane.
Okay, so AWS handles the burst.
Exactly. The ingestion buffering is handled at the VPC endpoint level, backed by AWS's internal network bandwidth. The structured fields are extracted in transit, allowing security teams to query the data immediately using logs analytics. It completely removes a highly fragile, distributed fleet of log collection nodes and replaces it with a scalable API endpoint.
That makes total sense. So to synthesize the architectural signals from all 41 of these updates, AWS is fundamentally changing how infrastructure operates.
Yes, they are.
They're providing strict hardware-level execution isolation with Firecracker-backed Lambda MicroVMs. They are enabling non-deterministic AI agents to operate securely across your account boundaries using Bedrock Agent Core memory, enforced by mathematically proven formal logic via the automated reasoning guardrails.
Right.
And simultaneously, they are removing the operational friction of managing this complexity by enabling zero downtime EMR updates, optimizing S3 backup event tracking, and completely eliminating the need for localized log collection agents with CloudWatch Direct syslog ingestion.
You now have all the necessary components for highly autonomous, self-healing infrastructure.
Yeah.
You have Lambda MicroVMs granting up to 8 hours of isolated execution state for AI-generated code.
Yeah.
We have Bedrock memory, allowing those AI agents to read, remember, and interact across multiple AWS accounts.
And the guardrails.
Right. You have automated mathematical verification, ensuring they don't violate strict security policies. This presents a specific architectural scenario for you to consider as you design your next system. Are we rapidly approaching an infrastructure paradigm where AI agents do not merely write code for developers to test and deploy, but autonomously provision their own isolated compute clusters and ephemeral networks to execute long-running tasks, continuously validating their own security perimeters along the way?
Wow, that is undeniably the trajectory these new primitives suggest. It's a lot to think about. Thank you for joining the deep dive today. Keep building, keep questioning the mechanics, and keep exploring these new architectures.